Okay, the reason we did the video on types of forces is because we need to know what forces are in order to create free body diagrams. And from here out, I'll often write FBD for free body diagrams. So you need to take notes as we go through this, label this section free body diagram notes, and here we go. The first thing we need to talk about is the difference between scalar quantities and vector quantities. A scalar quantity is anything that has only magnitude, so only a number value. I think temperature is the best example of this. If you think about temperature, if I say it's 50 degrees, there's no direction that goes with that. It's just 50 degrees. The same thing with time. If I say something takes 5 seconds, there's no direction with it. So be sure to write down that this has only magnitude. That means just a number. And here's some examples. Write those down. The difference is a vector quantity has magnitude and direction. So it's a number and a direction. For example, velocity is the same as speed, but it has a direction. So I'm going 30 miles an hour north. And you have to include the direction of it. Force is the one we're really going to be talking about here in free body diagrams. So for example, gravity is maybe 10 pounds going down. Or I'm pushing on something with 5 pounds of force going to the left. We always have a number and a direction on vector quantities. Be sure to copy this down. Okay, so now for free body diagrams. We represent free body diagrams with a visual. So we're drawing pictures, hence the name diagram. And in these, individual objects are isolated. So we take one piece and pull it away from everything else. For example, this is a pulley that has forces going up where the ropes are and a weight going down. Or this is a beam with forces going in the middle and on the ends. So we've isolated the one object all separate from everything else, and then we put our forces on there. A force is a straight line push or pull, and we already talked about the types. And it does have direction and magnitude. Remember, we had a column on the types of forces that talked about what direction each of those typical forces goes. We represent the direction with an arrowhead on it. And then the magnitude is shown by the length of the line. So something that's 10 pounds is twice as long as something that's 5 pounds. Something else we're going to talk about just briefly here is a moment that we're going to see come up later. Moments have to do with twisting things because not everything goes straight. Write down that a moment, this is clockwise, and CW stands for clockwise, and counterclockwise CCW. So this is like a force, except this is going in a circular pattern instead of a straight line. We did talk about moments before when we talked about torque. Moment is force times distance. So for example, if I push with a force here, the force has to be perpendicular to the arm. Here's the point where we're rotating it. And as we push on it here, the distance is perpendicular to the force. So a moment is just force times distance. All right, now we're going to specifically talk about free body diagrams. Here we have 3 books that are stacked up, and we're just going to say that each one weighs 5 pounds. And they're sitting on top of a table, and we're going to show you how to draw a free body diagram. You're going to need to draw this diagram on the next page. So here's how we're going to do it. First, we're going to make a sketch. And what are the isolated objects? Well, in our picture, we have this, for example, the top book. And we're just going to sketch it out as a little box. You do not need to be really detailed when you sketch these free body diagrams. So we sketch it out. Then we're going to put on the forces. And remember the types of forces we talked about in the last one. So here's our forces we're going to add. Well, this is the weight, the force of gravity of that top book pushing down on the one below it. Gravity is pulling the top book down. And then we have a normal force of the book below it pushing back up. Is there anything else acting on this force? No. We know the weight of the book is 5 pounds because it told us that in the problem. And the normal force pushing back up is equal to the weight. So that's our top book. For more complex free body diagrams, we may have to do some extra things such as lengths and heights. Notice that this one has some extra lengths added on here, some angles labeled on there, etc. We're not going to get to this kind of diagram for quite a while. We're going to be sticking with this kind for today. But I did want you just to see this kind. So here's our next picture. We're going to create a free body diagram for this little picture here. You're going to draw this in your notebook. Again, you don't need to draw this fancy picture. All we're going to draw is a little box that represents the sled. And what forces are on it? Well, we have the weight or the force of gravity. So here's another thing. You might use W for weight instead of force of gravity. Those are the same things. We also have the force of friction. If the sled is being pulled this way, friction always goes in the opposite direction. So draw this on your diagram. Would you expect the force of friction to be equal to the weight? No, this is probably smaller. We also have a normal force pushing back up on the sled. And then finally, we have the applied force where someone's pulling the sled along these ropes here. So there's our applied force. Notice it's put at the angle just like this is here. Here, whatever this angle is the same angle we draw on this side. Pause if you need to get this drawn in your notebook. Okay, now we're going to draw a free body diagram of someone pushing this refrigerator up this slope. And we're going to isolate out the refrigerator. So first we're going to draw our little square to represent the refrigerator. And what forces are acting on there? Well, I find it always best to start with gravity going down. And again, they're labeling it as W. You could label it as FG. And gravity goes straight down. Even though the refrigerator is at this funny angle here, gravity always goes straight down. Now the normal force is always perpendicular to the surface. Notice perpendicular is going to be like this. So when we draw it, it's got to be perpendicular to the surface this way. There's our normal force. And it's away from the surface, so it's going up at this angle. Then we've got the guy pushing the refrigerator. That's our applied force. There it is. And finally, we have the force of friction against the direction of motion and parallel to the surface. So there it is right there. Finally, we label in the angle, which happens to be this angle here, happens to be the same angle there. You could create a couple of triangles to figure that out, or we could have labeled it over here somewhere with the angle, that angle right there. So now I want you to do this one. So here's a pulley system, something that we learned about early in the semester, and we're going to create a free body diagram of this. So first, we're going to look at this mass right here. In order to create a free body diagram, we're going to do, there's our little mass, and what's acting on this mass? Well, always start with weight going down, the force of gravity going down. And then we have the tension in this cable pulling up. Now we're going to do the free body diagram of this pulley right here. What's acting on this pulley? Well, there's our pulley drawn. We have the weight of mass 2 plus the weight of the pulley pulling down on this one. And then we have the tension on both of those sides. Sorry, messed that up. The tension on both of those sides going up. Tension here and tension there. Notice that if I have one single cable attached to all this, the tension is the same everywhere in that cable. And if we're talking about free body diagrams, we have different types. We're going to talk about these later on in another unit when we get to trusses, so don't worry about this slide here. So here if we draw, I want you to draw this free body diagram. If we draw a free body diagram of this weight here, we'd have the weight of the object going down and then the tension in the cable going up. So draw this one. Now we have a sign with a weight W is hung by 2 cables. But notice this one's at this funny angle over here, and we want to draw a free body diagram. So here's our sign. our weight's going down, our tension's going this way, and our tension's going that way, and we'd be sure to put this angle on there. And that's what we need to know about free body diagrams for what we're going to accomplish today. Be sure you got all these notes down. Okay, thanks.